I think you should see this now. All right, so I want to talk today about the next generation AI, about what will AI look in the future beyond the best technology that we have today, which is, everybody agrees, I think, deep learning. We could have even better things than deep learning, and that's what I want to talk about. A few words about me. I am an expert in machine learning and AI. That's where I have lots of knowledge. Maybe this does not surprise you, but what may surprise you and what will become very interesting in a moment is that I also have a lot of knowledge about so-called wet neuroscience, meaning I have been a neuroscientist for many years at the Max Planck Institute, where I was performing experiments inside the brain, studying how the brain works. And this will be very important in a moment. But first, let us establish the fact that technology evolves. It never stops at some point, and then that's it. That's the end of the technology, right? So we will not stay forever with deep learning either. Right? So what we see here is a caricature history of our technology. And one thing that is very notable is that the technology expands exponentially. It means that it grows ever and ever faster. And the reason is that we build on the existing technology to develop new technology. And the more existing technology we have already, the faster we can evolve to new stages, right? So you shouldn't be surprised if we can improve deep learning as well, right? Here in this exponential curve, you can see on the left side that it took really long time to come up with stone tools, then bronze tools, then iron tools. We're talking here thousands of years. But then things got faster recently in the last few hundred years. And in the last few years, we have seen also rapid advancements of what artificial intelligence can do. And it's likely that this trend will not stop. And part of this trend is deep learning, right? So if deep learning reaches levels, maximum levels, saturations of what we can do, we need to come up with a new technology. And I will tell you now today, I am one of those people who develop new technologies, right? And I'll tell you all about it. Now, real brain, right? I said that a real brain will be important. And one reason is that we still did not match the human brain. The AI technology of today still is missing lots of things that a human brain can do. And here's a few of them. We need faster learning. Right? So machine learning technology today does not learn very effectively. It requires a lot of data, which equals slow learning, and has a problem of having to learn from all the data at the same time, right? So it takes lots of effort and lots of data to learn something, unlike humans who can learn very often from a single example. Right? The second problem is generalization. We much better generalize from the single examples we get, and these two problems are quite closely related. If we generalize better, we can learn better from small amounts of data. And then finally, accumulation of knowledge is one important aspect that also has to do with generalization and the speed of learning. And that is the fact that we, humans and animals as well, we can experience an event, learn from this event, the sample size being 1, and then we can add this knowledge to all the previous knowledge without having to rehearse the previous knowledge. And that's a problem still with deep learning. When we add new knowledge, we have to add it into the training data set and learn it together with the previous knowledge in order not to forget the old knowledge. Right? So here's one number illustrating the magnitude of this problem. An average person would need to live some 100,000 lives in order to be exposed to the same amount of language that one of the best large language models today, GPT-3 was exposed to for learning. And so the amount of language that a human gets exposed to in life and the amount of language the AI gets exposed to life there's a big difference between the two. Right? So we need to reduce those numbers for AI. There are also other nice to haves, maybe not immediately necessary things, not things that stick out as the most important ones, but also quickly become relevant. So, for example, locomotion. This we see especially in animals that it's very effective with fairly small brains. Animals are able to achieve very skillful actions, climbing trees, running away from predators, catching predators, flying. Imagine, just think of a squirrel and the skill that it exhibits with a really small brain, or a bird. That's kind of stuff we cannot do with today's technology. Then there's, of course, the problem of consciousness. The question of will machine ever be consciousness, whether machines need consciousness, whether we want it to have consciousness, or whether we have to make them conscious in order to match our intelligence. Long-term planning. Machines don't plan much in the future, but we do. And we can do lots of plans. We can have nested plans. We can plan for the near future, for the far future. We can plan for retirement. We can plan even for the generations behind after we are dead. This is all somehow integrated in our intelligence. Intuition. So this has to do also with small number of samples for learning. Sometimes without any samples of learning, we just have the feeling of what is the right thing to do, and very often we are right. And somehow this intuition is encoded in our genes and is telling us, giving us the directions of how to do things right, even without having to learn. Very important for survival, and it would be very useful for machines as well. Common sense. So I think a good example of common sense is a wild animal that lived in, say, forest its entire life, never seen a human home, and then by some accident, it enters a human home. Perhaps the animal is hungry and it's in the search for food, and the door was open and the animal enters. Now, a human home is nothing like anything else this animal has seen ever before. And yet, the animal is somehow able to use common sense to find food in this home, to search around, find the food, eat it, steal it, run away. And it's trivial, actually, for us. It's very hard for machines, very, very hard for machines. Imagine a robot that would be trained in a forest, and we put this robot suddenly in a human home and expecting that it would find its way around. Really, really hard. And finally, ethics. And we have also very good feeling, not perfect, but very good feeling on what is right and wrong things to do. And we also don't have to learn some of these things. And when we have to learn, we can learn them quite quickly. So why does it all matter? Where do we need all that? Well, I think practically, one problem is household robots. We do not have household robots today, yet we have been promised those in science fiction stories, right? And we don't have them. And I think the reason is that this is way too complex problem for deep learning. If you want to have an effective household robot that would be able to cook, clean, do laundry, and all the necessary errands that are there at home to be done, we need some better technology. And for that, we need to respect biology. And now I will tell you more about this gating technology that I'm developing. And I just want to point out first that this has come from my research in the brain. What you see here is my setup in my lab that I use to insert electrodes into the brain and to record from some 100 or even 150 neurons at the same time. And had I not done this research, the following technology would never come to me. I would never have had enough knowledge to come up with this technology, right? So I named this new technology gating, which I think will be next generation AI, because it will be getting one step closer to the way how human brains works. Like deep learning copies a little bit from the human brain. Gating copies a lot more. Now, an interesting thing about gating, you add gating, you add one thing, one principle, one new invention, and you get at the same time a solution to many different problems that are listed. So suddenly the machine is able to learn from small data. Suddenly the machine is able to generalize. It is able to accumulate knowledge. It's able actually even to reach consciousness, to learn how to do planning and be very good in locomotion in many other things. So in other words, I think gating is going to give us AI we always wanted. Now, second question, how quickly can we expect gating? And, well, we have to, again, remember that the growth of technology is an exponential curve. Right? So if you look at, you see here the graph of the time it took for acceptance of various types of technology, for getting a certain number of users. And you can see how these numbers also explode and become more and more faster. And ChatGPT recently being a great example of how you can go from 0 to 100 million in virtually no time, in a very, very short period of time. So new technology for instead of deep learning may also act suddenly very rapidly, right? Even though it's an exponential progress, much of this exponential progress always first happens below the threshold of, let's say, the threshold of public knowledge, right? There's lots of work that's happening behind that, right? The same was with GPT. There was lots of work going on before it became so successful and so popular, right? So when are we going to have it? I don't know for sure. I'll give you some more information in a moment about my assessments, my ideas, but I don't know for sure. Right? But I can tell you more where we are in terms of development of a technology, right? So, so for example, the theoretical and technological bases are the ones that are fairly good prepared. And by preparing those, there are two main challenges that need to be addressed, two groups of challenges. One is implementing gates. So taking basically connectivity of deep learning and turning this technology into gating technology. So expanding this technology with gates, adding gates, that this requires software, this requires mathematical conceptualization, this requires implementation. Right? Now, when you have that, then you have a machine that can perform gating. However, this machine has to learn. So you need the algorithms, systems, and everything for learning how to gate. Right? The classical learning mechanisms are not sufficient. They may be of some assistance, they may be helpful, but they're not sufficient. You have to develop a new learning mechanisms for it. All right. Now, a timeline of what has been done. So in 2015, I have published a general theoretical scientific paper that describes the principles of the development of this technology on a very abstract conceptual level. Like I use the theory, cybernetic theory and related fields in order to guide this development. In 22, so last year, I founded Roberts Governmental, a company that develops a new learning mechanism based on these scientific principles. So I first started with learning mechanisms and developing them before gating. So the learning mechanisms were developed not for gating because it wasn't implemented yet or developed yet, but for the classical machine learning, for deep learning. Right? And this is what Robert Gomental was doing. This year, I have published a scientific paper about the gating mechanisms, especially in how they happen in the real brain. I'll give you publications later if you would like to have references to this paper. Just most recently, I implemented gating in Python and in PyTorch. I'll show you some examples of the code as well. Also, this year we have finished the first round of collaboration with NASA using Robert Gomental using the learning technology and applying it to a foundational model for genetics for mice genome. And I hope in 24 to have the first demo of a full working system, meaning combining gating with learning. Right? And after that, at some point, the explosion should happen. When? I don't know. But at some point afterwards. Now, finally, maybe the most interesting part of the presentation, maybe some of you were asking, whether will I ever explain what gating is? I will explain it to you right now. Right? It's a whole new technology for machine learning. It's whole new, but it's based on connectionism, because as we know, the brain has connections, so we cannot get rid of it. Right? So to understand the gating, let us begin with the classical paradigm. I think everybody knows about that. This image illustrates here neurons and their connections and the basic idea on how connectionism works and therefore how deep learning works. Now, what gates do, they enrich these networks with so-called gates. And a gate can open or close a connection. So the lines that you have seen in the previous image. Now you have two examples here. You have one above line is the gate is closed. It means that the passage is done, can be through, and we put a green line, meaning like these signals are going through. On down, we have gate open. It means that the signal is not passing through, and we have a red light. This connection is basically closed to traffic. The gate is open, the connection is closed to traffic. Right? Now, these are two different philosophies on how to pass information from one set of neurons to another set of neurons. Right? So on the left, you have this classical approach where you have different weights, different strength of connections. So A to C is a weak connection, B to C is a strong connection. Therefore, B is more powerful in driving C than A. Right? On the right, we have what gating does, an illustration of what gating does, where we have basically the connections that are of the same strength. They don't have to be, they may be, but the gates open and close. And in this case, we have similar effect as on the left side because the gate above is open, no traffic, and below at the bottom we have a gate closed, and so there's a traffic. Again, B has effect on C, strong effect, and A in this particular case has no effect at all. So who opens and closes the gates? That's perhaps the next question. Right? And to understand that, let us consider that in such a network, we have, let's say, two layers that are connected with connections. And then for each particular gate, we identify one neuron whose activity opens and closes the gate. So it's very simple. The neuron is actually still works as a pattern detector. It detects a certain pattern. If the input reaches a certain threshold, there is an output, and this output may act on a gate. It may trigger a gate to open and close, whatever we set it up. Right? And each gate has its own neuron to close it and open. Right? Now, important thing is that first you have the activity passing through for neurons to calculate their activations, then you open and gates only after that. So why would you do after? What's the point? Well, the point is that you then as a second round, you run the the activity again, perhaps the same input as you have run it the first time, you run it for the second time again. And then you may have different network because the gates have changed the network. Now, in the second time, the inputs may again open and close some gates. So you have another third network and so on, right? And this is what happens in gating. You keep running over and over again. You never stop, and you keep changing the states of your gates. This has big implication on how we create our solutions, our AI solutions, right? So what you see here is a classical approach that we use today, where we have input on the left and the different layers of the network are passing information one to the other, right? So we have, this is a convolutional neural network, but the principle is similar for everything else. And this principle can be illustrated here a little better. So let's say we have an image of a grandmother, and the system needs to detect that this is a grandmother. So we have different stages of processing, and each stage detects some aspects of this image. So in the first early stages, detect simple combinations. For example, they may detect lines, pixels, and so on. Then you detect some more complex combinations of lines. Then later you may detect some even more complex components like a nose, mouth, eye, glasses. And then eventually you detect the entire category. And then the machine says, it's a grandmother, right? So this architecture that you have seen is basically fundamentally works on the idea that you look one and you pass this input through many, many, many different layers. And each layer has its own function. So you have basically lots of small neural networks chained into a chain, and each neural network has its own fixed function. And that's exactly what is not happening with gates. That's exactly not what's happening, guys, because in gates, we have one network only. We don't have so many different layers or networks. We have just one. But this one, we keep changing over time, right? So in the first round, when such a brain looks at the image, it does the early stage processing, detects the lines, rewires itself. Then it looks again. This rewired network does the next stage of processing and rewires itself more to detect more complex features. And then again, more complex features, and then again, and again, and again, until it is done and it recognizes the object, the category, for example. To illustrate how this may look, I have here a little simulated illustration. So let's say at the beginning, we have a network that is in its default state and all the gates are green. It means the information passes through. We present the stimulus, but nothing comes out. And the reason that nothing comes out is that at many places, there's a canceling out of positive, negative inputs to neurons, so nothing comes out. So you have to close some of those, either negative or positive. You have to prevent some of those inputs. So, but even though nothing comes out, internally things change. Some neurons get activated, and these neurons change gates and close some gates. So maybe this may be in the first round that you close some gates. Now the network looks once again at the same image, the grandmother, and it's a different network, different neurons get activated, and more neurons, the new neurons get activated. These new neurons again open some more gates, close the passage through the network, and so on. You could repeat it several times until you open enough of these clogging problems, and the network actually produces an output that says, I see the grandmother, right? So you can have a very short network. It's not anymore a deep network, it's a shallow network now suddenly. And this shallow network performs the function of a deep network in a somewhat similar way, but it's not having different pieces of trained network. It actually just rewires itself. Now, how do you add more intelligence, more capabilities to such a network? In deep neural networks, you often do it by extending the length of the chain. Here, you cannot physically extend the length of a chain because the chain is iteration based on iterations. But what you can do is you can actually extend the size of the network in the total number of connections, the total number of neurons that you have internally, the total number of gates that you have, and these kind of things. And now, the key learning problem, of course, in this network is how to know which neurons should open which gate or close which gate, when they should do it, in how long should the gate stay open or closed. So it's, as I said, it's a very different problem. It's not a problem that can be solved by the classical learning mechanism. And so we have to come up with new learning. One more thing that is important is that gating is also perfect for robotics, perfect for interacting with the environment. Because now when you interact with the environment, you don't have a fixed image, but every time you do changes to your gates, the environment may change because the environment is a dynamically changing word. Right? So you have interaction between the robot that is changing its gates and its way how it now sets up itself for this environment and the changes in the environment. Right? And this has to do with enactivism, which is a position in cognitive science that cognition arises through this dynamic interaction between the organism on one side and the environment on the other. So without it, you cannot have a cognition. Cognition is not an internal process like we have it in deep learning. Cognition is the interaction, right? By the way, this was summarized by ChatGPT from the Wikipedia page on enactivism. Right? Now, to see that, let me illustrate how this problem would be. Like, for example, this robot has a goal to reach this door on the other side of the room. Right? And at the first stage, the robot may be actually looking at several iterations on a fixed image, not moving at all, but setting up its own gates to make a plan. Right? So in the first round, it may detect objects. In the second round, it may detect spaces where it could pass through. In the third round, it may actually make some plan how to walk through and how to reach the door. And then it starts, and only then the robot starts moving forward. Now, after that, the robot starts moving forward. The image, the perception, the image that inputs that comes to the sensors of the door changes because of the moving of the robot. So the robot now has to adjust to the new input, but it is all based on the gates that it has already prepared and made a plan. Now, this previous plan, the network created through this previous plan, and the new inputs create a new network for the new action, and so on. And this is how it flows: the changes of the robot, the changes of the environment, and finally, the robot. If everything's right, the robot reaches the door. So we have one direction, then the other direction. Let me finally discuss consciousness, because I was explicitly asked to discuss this topic. Now, consciousness is really interesting. Right? First, I would like to point out that consciousness is something that looked like magic if we consider deep learning technology. With deep learning technology, we just have no way of even starting to think how possibly consciousness could be implemented in such machines. However, if we have gating, if we start thinking about gating, then there is actually ideas on how consciousness could be emerging. And even more than that, it turns out that gates have to start slowly reaching certain levels of consciousness in order to work effectively. And the reason for that is that, as I said, we have this clogging problem at the beginning, right? So the activity cannot pass through until the gates get it right. Right? So we have no much activity outside, or we have very little activity outside, and we have very rich, at the same time, we have very rich activity inside the network, because there's a lot more gates, there's a lot more neurons, there's a lot more connections inside than whatever can come out through the network. Right? Especially in robotics, where you have only very few actuators, you have very few muscles in human body. Like we have, I think, 170 something muscles, and then we have billions of neurons, and all of these neurons have a bunch of gates on their dendritic trees. Right? So lots of things are going on inside, and very little is coming out. And this dynamics that's going on inside through gates gives rise to consciousness, but not, of course, immediately, not with such a small network. You have to start with very simple knowledge, add more knowledge, and as the knowledge is growing, and as the network is growing in these directions, where you have more neurons internally, therefore more gates, more need to organize themselves, more need for them to negotiate some solution in order to produce output, the more our ability to be conscious about this activity, or this activity gives rise to consciousness, to higher levels of consciousness. All right. And I think this also can explain. I will not try to explain it today. I just will state that I think this can eventually explain how this gives rise to so-called qualia, so to the subjective personal experience that we all internally have. Right? So I think this image kind of illustrates it well. Like a machine without consciousness is just darkness. It doesn't experience anything. But then as consciousness arises, there is some light coming internally, some sort of experience arises internally. So this internal experience may be arising from the dynamics of interactions among gates. Or we could say consciousness emerges from continual iterations of gates. Now, what are the completion levels of this technology? Right? I try to assess those and give you some information here. How mature is the gating technology? So the concepts I put on 90%, so basic ideas, I think I have worked them out quite well, but you're never complete, so I put it 90%. Implementation. So I have implemented gates into PyTorch, as I said. I'll show you code in a moment. And but the learning mechanisms are not quite done, partly done, but not quite done. So there's needed some more work on the learning mechanism. Right? And demonstration, right? To be able to demonstrate it working completely, it's not enough just to implement everything. You also need to do lots of training. So I put demonstration to 30% because the only thing that I'm able to demonstrate right now are gating networks set up manually without learning mechanisms. So there is something to show, and it's pretty awesome, but it's not yet there, right? What I would like to have. Now I want to show a code snippet from PyTorch for implementing gating, just to have an idea how elegant things could be. And so what I've done here, I have overwritten a forward function in PyTorch, and some of you may know that this is the function that actually computes the process of flow of activation through the network. Right? And now, interestingly, in line 308, you can see that there is a matrix multiplication function between input and the weights of the network, which is just the standard stuff. But there is one more additional thing, and this is G weight, and G stands here for gates. Right? So the values, the G weights are multiplied with weights. So if the G value is 0, then this turns the whole weight into 0. So basically, this connection is closed for traffic. If the G value is 1, then you use the full weight, the connection is open for traffic. And of course, it could be somewhere in between. It could be half open, or it could be just ajar a little bit. Now, G weight could be 0.1, something like that. And in line 310, you see also that, no, the line 310 is the option just to use the classical application of deep learning without weights, without gates. But I wanted to say the line 314, I have applied gates also to bias. So we can gate also the bias parameter. So each parameter basically can get its own gate. That's how I implement. Right? What are the next steps? So as I said, learning for gates needs to be created. Then once this is all done, I would like to apply it to language data, right? So large language models have been very successful and very cool. Even without any gate, it will be really interesting to see what happens when you apply similar training paradigms to the networks of gating, right? And of course, the second very important field of application is robotics. As we said, gating is very important for robotics and very suitable for robotics. And especially autonomous driving is one very important field in robotics that I think should benefit greatly from gating. And this is all I had today. Thank you very much. Please contact me if you want to contribute in some way to that whole effort. And I'm open to the questions.
Thank you very much. Really, really great. Really enjoyed the presentation. Super interesting. Really excited about this topic. Yeah, then I would say, as you also said, let's switch to the Q&A. I would just make a start. I prepared something in advance. So my first question would be, the problem of deep learning very often is that it's kind of a black box, right? That you know, you throw something in, you don't know, can't really see control what's happening inside, and then you have an output. It seems like you kind of solved this here because they are not so just a few layers or one main layer, you said, right? So will we get rid of black boxes? Is it what you expect?
Not really. I mean, I agree with you that if you have fewer layers, it's easier to understand what's going on from input to output. Of course, it's very much easier. But what you have here now is temporal dependence, because the previous input makes the changes, and then on top of that, new inputs is processed differently, then it makes changes, and this accumulates over time. So the complexity is high. Complexity remains to be high, and it's not going to be easy to understand how the system has reached some state eventually, or made a certain decision. I can tell you from my own experience while programming this thing. So I built gating networks, trying to think how they will process and trying to figure out, you know, I put my own gate values and the rules for opening and closing gates in order to achieve certain effects. And I can tell you, I get confused very quickly, very soon. Only with few neurons and few gates, it's already mind-blowingly complicated. It's not going to be easy to do that. So we'll have to have learning mechanisms that learn that adjust them, and we'll have to just stand back and watch from the outside what's going on. From inside, it will be hard, I think.
All right. Are there any questions from the audience?
I have a question. Really interesting stuff. Thanks a lot. So I was wondering, how spread is this new technology across the AI community?
It's not spread at all. It's my secret. And we have, although the gating is completely new. I'm working on it, and only I have it. That nobody uses it yet. It's not ready yet even to be used. These learning mechanisms that we want to later apply for gating, and we have now, they are spread a little more. There are a few more places that are being used, but it's also very new. It's also very new, and it's at the beginning. Right? So it's all very, very new. It's not spread at all.
Are you allowed to talk about the NASA stuff that you are doing?
Yeah, I'm allowed to. I think so, because they are. We are writing a paper, and this is going to be published anyway. And they are government-funded agencies, so I think they're even obligated to write these papers. So I think I'm allowed to mention. So what we did, what the problem was, is that they wanted to train neural networks to take a piece of RNA from a mouse and be able to tell whether the mouse has spent some time in the space or not. So whether the DNA has spent some time in the space or not. Right? So basically, whether there are changes that exposure to radiation in the space leaves on DNA that is detectable by a machine learning algorithm. Right? So the problem was that they had only very small number sample. They in one mission with the space shuttle they would have 6 mice, right? And 6 is not enough for deep learning at all, right? So they were looking for ways to do that, right? So what we did is develop kind of like a big model for DNA, like kind of like foundation model for DNA or RNA, using data from Earth only, where you have much more data, and then use this learning algorithm for the system to learn how to learn. Right? After that, we applied it to mice data. So we would just then take 5 mice data. No, sorry. We would take data from one mission, a space mission, 6 mice for training, one condition in the space, another 6 mice from the Earth. They always had a control. They would put 6 in the space and 6 would remain in the lab on the down, right? And train this and then test on the next mission, right? A very hard problem. So it's not within the mission, it's across the missions. And that's basically what we did, right? So yeah, the paper should be out soon. It should have been out already, but then there are some iterations on writing, as usual. Everything takes longer. So,
I have a question, or maybe 3. Can you hear me?
Yeah, not very good on my end, at least.
yeah, I also don't hear very well.
I apologize. So I'll try to be slow. First of all, great talk. I love talks looking at the different architectures other than the current models. First question is, can you think of the gating as part of a feedback mechanism? Because what happened before will feedback and change the gates. Is that the right way to think about it?
I don't think so. I don't think so. I would think of gates, if you want to go like this one level more abstract explanation, I would think of gates as an inductive bias that you sort of you have a pattern detection system that tells you which inductive biases you should apply in this situation. So you use your pattern detection to say, I need this inductive bias, that inductive bias, and then you apply this inductive bias, and then you have a new network, and then you go in the next iteration for looking for more inductive biases.
I see.
Maybe that would be better. Of course,
so
if you put it in some loop. Yeah, please go ahead.
So it's maybe more like a sequential. It's for understanding sequences as opposed to kind of processing a static scene as it's trying to figure out the.
Yeah, I would agree with that. Yes, okay. It's more like that.
Okay. All right. And so then the other question is, have you done any tests on to see how scalable it is? So if you kind of increase the numbers of gates.
Sorry, I didn't hear that. Did I?
Yeah, I apologize. I'm from. Is it scalable? Have you increased the, to large numbers of connections, and is,
No, I haven't. I haven't. So practically, I don't know how it works when it gets scaled in practice. However, I did theoretical work in the background, and it should. The whole thing is designed to scale really well. And the reason for that is that basically, when you gate, you not only change the network, you also select a part of the network that is relevant and ignore the rest of the network. And so you're basically, even though you scale your network to say billions of neurons, at any given time, you are actually working with a subset. Right? So the scaling strategy is, let's have lots of resources, but at any time use a small subset of these resources. So that's why I think it should be scalable, yet to be proven. And the person is maybe gone, maybe not, I don't know. But
no,
you are here, it's just the camera is off.
Yeah, I turned off my camera here. I'll turn it back. Just because you said that you don't hear me, so I figured maybe that.
Yeah. Okay. Yeah. Or so it should be scalable, but it's not yet. I didn't bring it to scale because you need a learning algorithm. But without a learning algorithm, you do everything manually. You cannot scale manual stuff.
Makes sense.
I have a question about the data. You probably tested it. Which approach worked better, with the labeled data or with just unsupervised approach?
Did not test it. I don't think it matters, right? Because what you wanted, it's like, it's like using deep learning as autoencoder or encoder of your labels. It works well in both directions, both ways. So this is, the gating should be applied in a similar way, should have both applications in a similar way. Simply, you change the applications simply by changing how you use the network. You don't need to change much of the architecture, much of the principles. So I think both should work, but I still don't have anything to show to them.
Thank you.
I don't have a lot to show.
Another question, maybe not yet answerable, but if we think about normally implementing these neural networks in a company, let's say the major investment would be purchasing GPUs. Do you have any estimation on what the resource impact would be on of gating networks versus traditional?
All right. So I mean, the implementation I made was designed such that we could use GPU, right? As you have seen on PyTorch, everything, this code that you have seen, that can be easily just put on GPU. So that's nice. Now, would gating network solve about the same complexity of the problem with lesser resources? Yes, I think so. Yet again, as you said, I don't have a proof, but the whole thing was designed thinking through this problem, how to reduce the number of resources, how to make it more elegant, more simple, right? One way of intuitively to think about it is that instead of having lots of layers, each layer taking its own resources and doing a particular one job, you have basically just one layer that does all these jobs. And so maybe this one layer has some more parameters, is a little bit bulkier than each individual one of a classical network, but still it's much smaller, right? So it should reduce the resources, and both computational resources and memory resources. Right?
Okay, thanks a lot.
The question is, how can the AI community support the big data collation for potential scaling?
I didn't hear one word. How can
the AI community support the big data collation for potential scaling of your approach?
Well, I mean, in general, if you want to support, I would be very happy to have any kind of support here. Anyone who is interested in can write to me, can join. What I would recommend as a starting point is reading the papers. There's some papers out. Actually, maybe since I'm still sharing my screen, I can show you some of the publications. If you are interested, you may want to make screenshots. So this is a paper about brain physiology, which physiological aspects in the brain should be doing gating. I think it should be really interesting to look at it, to read it. Then this is archive paper from Roberts Go Mental about this learning technology. So this should be also interesting to read. And also, fundamentally, who wants to go through the pain of a hard theoretical paper from 2015 that I mentioned? Then you could read this paper as well. So what I would recommend is reading, getting informed, getting some feeling, and judging for yourself whether you want to help me, or you want to go there or not. Right? And if you do, please contact me and tell me, how would you like to help out? In which way? Like, there's so many different ways to do it, right? From business, from technology, from science, from implementation, from marketing, from data collecting, preparing data. There's a few other things that I did not describe what are needed for good training, and maybe I could mention now. So, I mentioned that we need to accumulate knowledge, right? But accumulation of knowledge does not come randomly. Like, if you think how we biologically learn, we have to first learn basic things, some basic fundamental things, and then on top of them, we learn more complex, more complex, more complex. Like, we first learn counting in order to learn addition. And we have to learn addition in order to learn multiplication. And we have to learn multiplication in order to learn power operations in mathematics. And it has to go exactly in this order. Like, that's the educational structure. Now, for gating networks, they need exactly this. You cannot just throw all the data at them, as deep learning does. You have to actually break the data down into organizational structure. So that's one thing that really will require lots of work. It's like, like a teacher in a school. You have to think, like, what my students need first in order to prepare them for the next, That's going to be hard work on our human side in order to train this network properly, because that's the only way how they can learn effectively. Right? That's something to help. There's going to be lots of work on that. Lots of work. There's another paper I wrote, actually a document I wrote about this type of problems of learning. It's called AI Kindergarten. So if you Google AI Kindergarten, I did not prepare a slideshow for that, but it's also relevant. So please inform yourself, get a little bit into it, and if your interest is high, I'd be very happy to talk to you more about it.
So I have actually many questions, but maybe just one question. You mentioned that your proposed model will generalize better than existing models. If I understand correctly, after training, the model will have a certain fixed form and structure maybe. So how will it be able to generalize better than other models? How will it change when facing a new situation?
All right. Yeah, that's a very good question. And I have to admit, I don't have a very simple, very good, very simple, intuitive answer like that you would say, yeah, clear. I have a very, very convoluted scientific answer to that. So maybe, I'll bear with me and I'll walk you through that. Right? So what we have noticed with classical models is that they learn really well. They learn with small amounts of data when the problems are simplified and when the models are small. So meaning you have small number of parameters and to train, and then it's enough to have a small amount of data for the model to learn the task. But there's one more pre-requirement, and that's the model architecture already has to be such that it is suitable for the task that you want to learn, right? So you have a model that's suitable for the task, like the architecture. You have a small number of parameters. If you have these two conditions, then you can learn from small amount of data. And if you learn from if you have all this, you can say that the model has a state that as if it's generalizing really well from the data for this particular problem that it has been prepared for, right? Now, what you want to have is such situation dynamically emerging within the gating network. Like you have a huge gating network, but what's happening in the process when you have opening and closing of parts of the network, what will happen is that the big chunk of the network will be closed, and a small part of the network will go through, will actually produce results, right? And this small part will mathematically be equivalent to what I have just described. It will be a small network, well adjusted to the problem, and will have only a small number of parameters that you need to adjust. Right? And that's the idea, is that exactly this happens in our brains. That's exactly this happens when we learn things, when we generalize things. Like we have so much knowledge that you acquire through the lifetime, but when you learn a new fact, you learn just about that. You don't address the rest of the knowledge, right? If you need to learn, like in a city, you're in a city and somebody needs to explain to you how to find, I don't know, gas station, right? Turn left, turn right, you will see big red building just behind them. You need just these pieces of information. All the rest of your knowledge, entire history, literature, math, science, whatever you learned in life, everything's untouched. Because the gates have closed and opened the right thing, that you just have this part activated. And that's what generalized allows for the effective generalization. I hope this was at least somewhat clear.
Yeah, thank you. That was interesting. So I think the way I think about it is having a very big, capable network, but then basically depending on the data, you train the right parts of the network, very specific parts, and perhaps along the learning path you have described earlier in a more systematic way, and in that way achieve kind of solve this optimization problem of training the weights more globally, let's say. So reaching maybe better local optima than right now, and eventually, yeah, having a better model. So
yeah, I think this is quite accurate what you said. I think this is quite accurate, right? So although you have a huge network, you narrow down a very small subset, and that you learn only here. The rest you don't touch. Right? And which part you will learn depends on the gates. The gates decide what will be learned. They decide where the information is going to go through. And wherever it goes through, it learns. Where it doesn't go through, it doesn't learn.
And because of the iterations, the gates also depend on the data, right, that you use to learn.
Exactly. It depends, of course. It depends on the data, depends on what happened before, where you have been before.
So then I imagine that the training will also be very difficult, since you have these iterations and you need to make sure that they converge. I guess so. This can be challenging, I guess.
That's a very good point. It can be challenging, and it's a really interesting thing. Like this is a part where we can intuitively think really well about this challenge. So I was asked just a minute ago, like, are we going to understand, have intuition, how it works? No, we will not, except for one part, for this challenging part. Whenever it gets challenging, that's where we have a really good intuition how to cope with this challenge. And the reason is that exactly these challenges in our own minds are the ones that give rise to consciousness. Right? What we are conscious about is the challenges of convergence. If things converge well, it just passes by unconscious. If things start not converging in our head and they keep like problematic and they cannot converge, that's where we start being conscious about stuff. Right? So we will have a good intuition, right, about it. So why is it important? It's because we can ask ourselves, okay, how do we solve these things? Which strategies are good for solving these things? And we can then apply similar strategies to resolve these challenges in the neural networks. Right? That's about the only thing that we can solve well, that we have a good intuition, because we have conscious access to that. It's really interesting. It's really, I don't know, but mind-blowing for me, this idea.
I wonder if I can ask one more follow-up question. This is Smitty, by the way. And the question is, how do you plan on kind of benchmarking and comparing with the traditional?
Well, I don't have very detailed plan on that, but probably you would have to take some similar task that has been solved, well solved with the classical neural network, and compare the amount of data for training that you needed to achieve certain performance. That's, I think, number one. And number two, you would need to compare the total number of parameters the network has, the resulting network has, that achieves the same performance, right? So, for example, let's take the classical simple MNIST problem, right? So today, best models are almost 100%, but not exactly, 99.7%, right? And they have, I don't know, a couple of millions of parameters. And they use the entire MNIST plus some synthetic data derived out of the training data set, right? So let's say you get the same performance, but you have 10 times smaller model and 100 times less data. You just take a 1/100th of the training data set. So that would be something I would hope to be able to show. But it's lots of work to get there. So I need help as collaborators